Okay, y'all, let's talk about oxidation numbers. Before we start, remember that covalent bonds are between nonmetals and ionic bonds are between a metal and a nonmetal. Or a metal and a polyatomic ion. And remember, polyatomic ions are covalently bonded atoms that do have a charge. So what is an oxidation number? Oxidation numbers help us to keep track of electrons. Full charges can only exist on ions, but any kind of atom can have an oxidation number. So for ionic compounds, the oxidation number is the charge. If an atom is part of a covalent bond, either because it's in a covalent compound or within a polyatomic ion, the atoms share electrons, but probably not equally, kind of like we see here with the oxygen and the hydrogens that are bonded together in a polar covalent bond of water. In these situations, the oxidation number is showing the distribution of electrons, kind of like a fictional charge. So the more electronegative element will have a more negative oxidation number, while the less electronegative element will have a more positive oxidation number. We have some rules for assigning oxidation numbers, and they're a little bit different for ionic compounds than for neutral compounds. If we have an ionic compound and it's a monoatomic ion, the charge is its oxidation number. So for example, if we have a magnesium ion, that's just one atom with a charge, its oxidation number is going to be +2. And you can do the +2 or 2+, it doesn't matter what order you write it in. If you have a polyatomic ion, the oxidation numbers must combine to be the charge of the polyatomic ion, which is what we have set up over here. So let's pretend that this is a polyatomic ion, that we know we have 2 of atom X and 3 of atom Y, and the overall charge is -1 of that polyatomic ion. To set this up, we'll do 2 times atom X plus 3 times atom Y is equal to -1. And then this also tells us that we know that Y's oxidation number is -3. So that'll lead us to 2x plus 3 times -3 is equal to -1. So 2x minus 9 equals -1. And then to get x by itself, we'll add 9 to both sides. 2x is equal to +8. So x's oxidation number is going to be +4. For a neutral compound, the sum of the oxidation numbers in the overall compound is going to combine to be 0 because it does not have a charge at all. So instead of setting it equal to -1, you would set it up equal to 0 if you needed to figure out one of the oxidation numbers. So for these other rules, we're going to follow them in order. If we put some numbers beside them, if this was 1, 2, 3, 4, we're going to go through these steps in order. So first we want to check, is the element by itself? If so, its oxidation number is 0, and that would be neutral. And that includes diatomic elements like nitrogen, hydrogen, oxygen, fluorine, chlorine, bromine, and iodine. Step 2, does the compound or polyatomic contain fluorine, fluorine always has an oxidation number of -1. Step 3, hydrogen, it's going to most of the time have an oxidation of +1. Rarely, its oxidation can be -1 if it's bonded only with a metal in a metal hydride, like lithium hydrate. So that leaves us with step 4, oxygen. Oxygen is going to mostly have an oxidation number of -2, but rarely it can be a -1 if it's in a peroxide group, such as hydrogen peroxide, or it can be +2 if it was with fluorine in oxygen fluoride. So that's where we're following the steps in order, because the fluorine would always get its -1, and that would change oxygen's oxidation from what it normally is as -2. So let's do some of these examples together. If we look at this sodium, sodium is by itself, so it's going to have an oxidation number of 0. Usually we write the oxidation numbers above the element, kind of like we did the charge, but just more centered. And so that's following rule 1, the element is by itself. Next, we're going through the steps. It's not by itself, there's not a fluorine, there's not a hydrogen, but we do have this oxygen, so it'll have an oxidation number of -2. Now we need to figure out the oxidation number of the sulfur, and notice this has an overall -2 charge. So sulfur plus 2 oxygens that have an oxidation number of -2 will be equal to -2. So sulfur minus 4 is equal to -2, which means sulfur's oxidation number is +2. Then we've got sodium carbonate. Let's look at the ionic charges of these, since we have a metal and a polyatomic ion. So sodium has an ionic charge of +1. Carbonate has an ionic charge of -2. And we'll just write that those are the ionic charges as a reminder. So we'll give sodium its +1, and then when we look within the polyatomic ion, we'll give oxygen its -2. But we need to figure out the carbon's oxidation number. So carbon plus 3 oxygens that have a -2 oxidation number will be equal to -2. So carbon minus 6 is equal to -2. So carbon's oxidation number will be +4. Next, we've got iron 2 nitrate. If we're looking at the ionic charges, the iron has a +2 charge. Remember, we swap and drop the charges to become the subscripts. And then nitrate always has a -1 charge. So we'll go ahead and give iron its +2. We know that oxygen is a -2. We need to figure out what nitrogen is. So nitrogen plus 3 oxygens that have a -2 charge is going to be equal to -1, which is nitrate's overall charge. So nitrogen minus 6 is equal to -1. So nitrogen's oxidation number is going to be a +5. Take a minute, pause the video, see if you can figure out the you-dos before we go over the answers together. Alright, so if we're going through the rules, oxygen has a -2. We need to figure out the sulfur. So sulfur plus 2 oxygens that have a -2 charge is going to be equal to 0. This time we're setting it to 0 because this compound doesn't have an overall charge like it did up here. So sulfur -4 is equal to 0. Oops. So sulfur's oxidation number is going to be +4. Next, with chlorine, that's just an element by itself, even though it's a diatomic, so its oxidation number will be 0. Next, we've got an ionic compound, so we'll give potassium a +1 charge because that's a group 1 metal, and then permanganate has a -1 charge, which we could look at the back of the periodic table for its charge, or we know because there's not an overall charge on this compound, if potassium is +1, then the permanganate has to be -1. So we'll give potassium its +1 oxidation number, we'll give oxygen its -2, and we need to figure out what manganese is. So manganese plus 4 oxygens that have a -2 oxidation number is equal to -1. Manganese -8 is equal to -1. So manganese's oxidation number will be +7. And then last but not least, with ammonia, the hydrogen for rule number 3 is going to be +1. We need to figure out what nitrogen is, and it's got an overall +1 charge. So nitrogen plus 4 hydrogens with a +1 charge. All of those were negative, so I'll just do this. And so nitrogen plus 4 is equal to 1. So the nitrogen will have an oxidation number of -3. And what you might notice here is that nitrogen in this compound has an oxidation number of -3, while in this compound it had an oxidation number of +5. So that leads us to the next page, where we're looking at the difference between oxidation number and charge. An element can have a common charge as an ion, but it can have a variety of different oxidation numbers if it's a part of a covalent bond. So for example, here, carbon is by itself, so its oxidation number is 0. Then, when it's bonded in carbon monoxide, the oxygen has a -2 oxidation number, which means the carbon has to have a +2 oxidation number. So carbon does not always have the same oxidation number. We can go even further by looking at carbon dioxide. The oxygen has the -2 oxidation number, and there are 2 of those, so this carbon has to have a +4 oxidation number. And then even oxygen, it's not always -2, because if it's by itself, like it is here, its oxidation number is 0. Alright, so take a minute and stop right here. I want you to look at the top 2 reactions on practice 11.1, and I want you to assign the oxidation numbers to each of these atoms in this reaction, and then come back and we'll check over those. Alright, so before we get into those answers, let's take a look at what a redox reaction is. A redox reaction is a reaction where the electrons are moving from one atom to another, gaining and losing both at the same time. And that's what we call oxidation and reduction, and then we just abbreviate it to say redox. So when reduction happens, it seems kind of backwards, but that means that you're actually gaining electrons. Because electrons have a negative charge, the more and more negative electrons you have, the lower and lower the oxidation number is going to become, or the more negative it will become. Oxidation, on the other hand, is loss of electrons. So the more and more electrons that you lose, your oxidation number is going to become more and more positive. A couple of ways to remember the which is which are the acronyms oil rig or Leo says Ger. Oil rig stands for oxidation is loss of electrons. Reduction is gain. So oil rig, and then Leo says Ger is losing electrons. Is oxidation. Gaining electrons is reduction. So whichever one you prefer, whichever one helps it stick in your mind a little better, go with that one so that you can remember the difference between the two. Oxidation cannot occur without reduction or vice versa. If something is losing electrons, then the other thing has to be gaining them, or vice versa. So now we need to see, is it a redox reaction? You can see here that I added the oxidation numbers after going through the reactions on the other page. I can also balance the equation by adding the coefficients in. So now, to tell if it's a redox reaction or not, we're going to look to see which oxidation numbers change. So if we start with copper, in the reactants, its oxidation number is 0, and in the products, its oxidation number is +3. So it went from 0 to +3. It's getting more positive, so it lost electrons, which means it was oxidized. Then, if we look at silver, silver started +1 and then became 0. It's getting more negative, so it's gained electrons, which means it was reduced. Then if we're just checking, nitrogen in the reactants has a +5 and in the products a +5, oxygen stays at -2 as well. So this is a redox reaction because we had an atom that lost electrons and an atom that gained electrons. For number 2, it's easy to balance this one because all of the coefficients are 1. Now let's look at the oxidation. If magnesium started at 0 and then ended at +2, it lost electrons, it became more positive, so it was oxidized. Then if we look at copper, copper started at +2 and then went to 0. So it gained electrons, it became more negative, so it was reduced. And then just to check, the nitrogen was +5 on both sides and oxygen is -2 on both sides. So this one is also a redox reaction. Take a minute, pause the video, see if you can do number 3 yourself. Alright, this one's pretty easy because you've got 2 elements that are by themselves. So both of those have an oxidation number of 0. And then oxygen always has a -2. There's 3 of those. So with 2 aluminums, they each have to have a +3 charge, which if you remember, aluminum is one of the transition metals that always has the same charge, which is +3. And then to balance it, we'll just do 1, 2, 3. So when we look at aluminum, it starts at +3, and then in the products goes to 0. So +3 to 0 means it's gained electrons, and if it gained electrons, it was reduced. What's that? Aluminum. Then when we look at oxygen, it started off at -2 and went to 0. So it lost electrons, which means it was oxidized. So again, another redox reaction. Now, we finished notes, so what I want you to do is go through practice 11.1 and continue to answer the questions in section 2. A says to predict the products if necessary, so that's what you'll do for number 5. B says write the charges or oxidation numbers above each element or compound. Determine which was oxidized, which was reduced, and then also balance the equation. Let me know if you have any questions.